Welcome to the Perimeter Institute PSI graduate course on classical mechanics, a geometric formulation taught by David Kubizniak. The course has 7 lectures. We will rediscover the mechanics you already know through the language of geometry. This is a short course guide. This is a master's level course on advanced classical mechanics. It assumes you have already met Lagrangian and Hamiltonian mechanics as an undergraduate, including the Euler-Lagrange equations and Hamilton's canonical equations. Its special feature, everything is rewritten in a coordinate-free geometric form, valid in any coordinate system. The first lecture states 3 goals. First, review classical mechanics as you know it, the Lagrangian and Hamiltonian pictures. Second, learn some differential geometry, manifolds, tangent spaces, vector fields, and the Lie derivative. Third, and most importantly, use this language to describe mechanics geometrically. In short, mechanics upgraded from coordinate calculations to geometric structures. Why is this language worth learning? The familiar Hamilton's equations depend on coordinates q and p. On a symplectic manifold, the same dynamics becomes an intrinsic relation between the Hamiltonian vector field and the symplectic form, valid without choosing coordinates. This is the language of general relativity and modern theoretical physics. Once learned, canonical transformations become natural properties of geometric objects. The course has 7 lectures in 2 parts. The first 4 combine mathematical preparation with a mechanics review. Lecture 1, Introduction, Lecture 2, Manifolds, Lecture 3, Tangent spaces and the Lie derivative, Lecture 4, Lagrangian mechanics in geometric language, with a Hamiltonian review. The last 3 form the geometric trilogy. Lecture 5, Hamilton, Jacobi theory, and canonical transformations. Lecture 6, Symplectic geometry. Lecture 7, Time-dependent mechanics and contact geometry. Lecture 1, the Introduction. Classical mechanics, the lecturer explains, can be beautifully described by symplectic geometry and contact geometry. The Euler-Lagrange equations and Hamilton's canonical equations will all appear in invariant geometric form. This lecture is the map of the whole course. Remember the 3 goals. Every later lecture serves them. Lecture 2. The definition of a manifold. A manifold is defined intrinsically, using only things living on it, with no reference to an external space. Every point is covered by open sets, and each open set is mapped by a chart to an open subset of n-dimensional Euclidean space. Locally, it looks like ordinary space. Together, the charts cover the manifold. This is the idea of an atlas. This lecture is the mathematical foundation of the course. Lecture 3, Tangent spaces, vector fields, and the Lie derivative. The core difficulty, vectors at different points live in different tangent spaces, so how do we compare or differentiate them? The breakthrough is the one-to-one correspondence between a vector field and its integral curves, which leads to the Lie derivative. This is the most concept-dense lecture, the toolbox for everything that follows, and it is worth watching twice. Lecture 4, The Bridge. Lagrangian mechanics lives on the configuration space. Each point is one configuration of the system, and a curve is its time evolution. Extending to the twice as large phase space brings us to the Hamiltonian picture. Starting from the next lecture, the differential geometry tools officially take the stage. Lecture 5. Hamilton-Jacobi theory and canonical transformations. Classical mechanics has 3 equivalent descriptions: the Lagrangian picture, the Hamiltonian picture, and the Hamilton-Jacobi picture, where a single partial differential equation governs everything. A canonical transformation freely changes the phase space coordinates while preserving the form of Hamilton's equations, and this freedom leads to generating functions. Lecture 6. Hamiltonian mechanics in symplectic geometry. A symplectic manifold is a manifold equipped with a closed, non-degenerate 2 form. It is totally antisymmetric, exactly the opposite of a metric. The highlight? Time. Independent Hamiltonian mechanics is simply geometry on an even-dimensional symplectic manifold. The course even includes computer algebra exercises to build your intuition. Lecture 7. The finale. Symplectic geometry only describes time-independent Hamiltonians. How do we bring time back? The answer? Go beyond symplectic geometry into odd-dimensional contact geometry. Time-dependent Hamiltonian mechanics then finds an equally beautiful formulation on the extended phase space. After this course, you will take away 3 geometric languages: differential geometry, symplectic geometry, and contact geometry, and a deep understanding that mechanics is geometry. Watch the lectures in order 1 to 7. The tools of lectures 2 and 3 are the foundation of everything that follows. The videos come from the Perimeter Institute website. Now, let us begin Lecture 1.